In this video, I'm going to give you an introduction to how to determine molecular shapes from the Lewis structures of molecules. We're going to start with an example, dichloromethane Ch2cl2. When you draw the Lewis structure of this molecule, you'll probably get something like this. At least this is the way I draw it every time. Put in our lone pairs. Notice that the way we draw the Lewis structure has the atoms, of course, all in the plane of the paper. That's the easiest way to draw it, sort of in a diamond or square shape. If this actually represents not only the Lewis structure, but the three-dimensional structure of the molecule, in other words, if it really is flat like this, then we would expect there might be two forms of Ch2cl2. And the reason is because I can redraw this with the chlorines on opposite sides of the carbon. And this way of drawing it is distinct from the first one. In other words, I can't overlay these two structures. No matter how I rotate them around, I wouldn't be able to get them overlay, which means they're actually distinct molecules. So if the true three-dimensional shape of this Ch2cl2 is flat like this, we would expect to be able to isolate two forms of the molecule. One in which the chlorines are sort of next to each other, and one in which the chlorines are on opposite sides. However, experiment shows that there's only one form of Ch2cl2. And what does that mean? Well, it means that this is probably not the correct shape. So what is the correct shape? Well, there's another way to arrange these atoms, and it takes a little bit of a more three-dimensional view, because we're not going to draw it flat. We're going to draw it with as shown here, with the you can see the bonds are now drawn as wedges and dashes and then sort of regular lines. The wedge, the one for the bottom chlorine, means that chlorine, or that bond, is coming out of the plane of the screen at you. And so you're supposed to imagine this three-dimensionally with that one sort of coming out at you. The dash is supposed to indicate a bond which is going back behind the screen slightly. And then just regular straight lines like the one to the top hydrogen mean lines that are sort of in the plane of the paper, in the plane of the screen in this case. Drawing it this way, arranging the atoms in this fashion around the carbon, they make sort of a little pyramid, with the bottom hydrogen and two chlorines forming a sort of a trigonal base, a triangular base to the pyramid, and then the top hydrogen sort of at the peak of the pyramid, with the carbon in the center. Now, for this particular arrangement, which is called a tetrahedron, no matter how I arrange the atoms, I end up with only one molecule. And the reason for that is that, let's say I redraw it like this, with the chlorines sort of looking like they're more on opposite sides. They're really not. And the reason that I know is because if I draw an axis down the center right through this tetrahedron, and then rotate around that axis as shown, the hydrogen will move to that chlorine position. This chlorine will move to the other chlorine's position, and then this chlorine will move to the hydrogen position to produce that very same molecule. So these are the same. So even though it looks like I've moved the atoms around, what we get is actually the same structure. And in fact, no matter how we arrange the atoms around this tetrahedron shape, they will all end up being the same, all superimposable, which means they're the same molecule. So we can only get one Ch2cl2 using this particular shape. And so this is probably the correct shape. Well, this could have been predicted using a technique or theory called valence shell electron pair repulsion. Valence shell electron pair repulsion. And basically what this means is that the valence electrons, which are the electrons in bonds and lone pairs, and in particular we're looking at the ones around the central atom, the ones on the terminal atoms like on the chlorines in this case, don't matter. The electrons in those pairs, of course, are negatively charged and repel each other. Like charges attract, or opposite charges attract, and like charges repel. So based on the fact that they're all negatively charged in those bonds, they'll want to get as far away from each other as possible. So going back to that first structure that we drew, I'm going to put little orange hazes here to represent the electron clouds in those bonds. Right now, as drawn, those are 90 degrees apart. But that's not the furthest we can get them, and so VSEPR would predict that this would not be the correct structure. It would in fact predict that our tetrahedron would be the correct structure, because that's the furthest away I can arrange 4 electron pairs around a central atom, is in that tetrahedral arrangement, which results in angles of 109.5 degrees. So of course that's further apart than 90 degrees, and that's going to be more stable at relieving the negative repulsion from the electrons in those electron pairs in the bonds. And in fact, we can use this electron pair repulsion theory to predict the structures when, and we're going to do this in the cases of having 2 up to 6 electron pairs around the central atom. So let's look at another example that has just 2 electron pairs around the central atom, and that's beryllium chloride. In the gas phase, this is a molecular BCl2. I'll draw the Lewis structure for this. Beryllium is electron deficient, that's okay. Drawing the lone pairs around the chlorines. But keep in mind, those lone pairs around the chlorines don't matter. It's only the pairs of electrons around the central atom. Okay, so in this case the beryllium. Now as I've drawn them, those electron pairs have significant repulsion. They're only 90 degrees apart. And they would like to get further apart than that if they can. In which they can in this case, because, and that the red there indicates the electron pair repulsion, I can move this bond over from the way I've drawn it originally in the Lewis structure to be further apart. And move it, say, 120 degrees. But since there's only 2, that's not the furthest way I can get it. I can actually get these bonds, or electron pairs, and the bonds to be 180 degrees apart. And that's the furthest away they can get from each other. And so in fact, that is the predicted structure for beryllium chloride. And in fact, it's the right structure. And in all cases in which you have 2 electron pairs around the central atom, the geometry of those electron pairs will be in this linear arrangement with 180 degrees distance between the electron pairs. So let's look at that for just a sort of a generic molecule. So this is any old molecule. Those lines, so those 2 lines represent either lone pairs or bonding pairs around the central atom. They will get as far away as possible, which is 180 degrees, like so. Let's just redraw our example. Okay, what about for 3 electron pairs around the central atom? Well, for this we're going to use the example of boron trifluoride, which has this Lewis structure. Okay, this is almost always the way I draw the Lewis structure, in fact, because I'm not thinking about shape initially when I draw my Lewis structure. You can see we have sort of 2 fluorine-boron-fluorine bond angles of 90 degrees, and then one side of it with a much bigger angle of 180 degrees. Now, based on valence shell electron pair repulsion, all those pairs will like to try and get as far away from each other as possible. In this case, the furthest away we can move them is to arrange them symmetrically in the plane of the paper and as far away from each other as possible, which is 120 degrees. So for 3 electron pairs, we get what is called a trigonal planar geometry with 120-degree angles between all the electron pairs. Now we use the BF3 molecule. All of those electron pairs are bonds, but this geometry would also occur for any central atom that had 3 electron pairs, be those pairs bonds or lone pairs on the central atom. And we'll talk about how lone pairs affect shape in the next video. So let's put in our little generic drawing. For a trigonal planar structure, you should draw your central atom. That's the gray sphere shown. And then arrange your 3 bonds in the plane of the paper, so just regular or straight lines as shown, 120 degrees apart. And then we'll just put spheres in there to make it feel better. Okay. And there's our sample molecule. So trigonal planar. Now we already went over the case of 4 electron pairs on the central atom. In that case, they arrange themselves 109 degrees, 0.5 degrees apart in what is called a tetrahedron geometry. To draw this, it takes some practice, but you're going to draw your central atom like that, okay, and then you'll have one line just in the plane of the paper, sort of a little bit angled down, one wedge coming out like that, so that's an electron pair that's sort of coming out of the plane of the paper, and then a dashed line going back, that indicates an electron pair going back, and then another line straight up and in the plane of the paper. And that looks like that. We'll put some atoms on the end of that, and it forms a little pyramid, which we call a tetrahedron. The tetra meaning the 4 sides of this geometric shape. A good example molecule would be methane. The hydrogens attached through those 4 bonds, those 4 electron pairs, those electron pairs move as far away from each other as they can get, which ends up being 109.5 degrees and the tetrahedron shape. Okay, so what about 5 and 6? Well, for 5, the geometry, the furthest away the electron pairs can arrange themselves is what is called a trigonal bipyramid structure, which ends up having 2 bond angles between the electron pairs, 90 degrees and 120 degrees. And let me just show you what that looks like really quickly. It looks like this. The structure has sort of a triangle in the middle, like a base, with a pyramid going up and then a pyramid down. You can see there's 5 electron pairs around that gray central atom with 120 degree angles between the pairs that are in the sort of the triangular plane in the middle, and then 90 degree angles between the electrons that are in the vertices going up and down. So how do you draw that? Well, the way I usually start is by drawing sort of a triangle. I make it with sort of a line in the plane to the left, a wedge, one wedge coming out, one dashed line going back, so to simulate a triangle that's sort of coming in and out of the plane of the paper, or in this case the plane of the screen. Then a line up and down for the vertices for those electron pairs that are going up. And that makes that bond angles that we talked about, 120 degrees for the triangle that's sort of coming in on the paper, and then 90 degree bond angles for between the electron pairs in the triangle and the ones that are up and down. And that's a trigonal bipyramid. Bipyramid for the 2 pyramids that are going up and down above that triangle that's formed in the center. And then finally, 6 is an octahedron shape, or octahedral. The furthest away you can get 6 electron pairs arranged around the central atom are 90 degrees apart. And that ends up being what is called an octahedral shape. To draw this, you start by drawing a sort of a square arrangement, two wedges coming sort of out at you and two dashed lines going back to make sort of a square base. And that square should look like it's coming sort of in and out of the plane of your screen, like that. So wedges out, dashes going back. And then there's two electron pairs above and below forming vertices. And what this makes then is the base with a square pyramid up and a square pyramid down. And then octahedron names comes from the fact that there are 8 faces to this particular geometric shape. So it makes a little sort of 8-sided geometric shape, thus called octahedron. So I encourage you to practice drawing these shapes as much as possible, these geometric arrangements, and we'll talk more about how to convert Lewis structures into these geometric shapes and more shapes based on them in one of the upcoming videos.